Okay, now we want to start talking about batteries. Batteries are something that you're going to deal with your entire career. It really doesn't matter what type of aviation you get into, be it GA, rotary wing, heavy commercial, military, space, whatever. Batteries are everywhere. We have to have some sort of way to store power so that way we can start things, run things in standby mode, run things in emergency mode, and whatnot. There's two basic kinds of batteries. There's a primary cell battery, and then there's the secondary cell battery. Now, you're all very familiar with the primary cell battery, whether you know it or not. They are batteries like your AA's, your AAA's, your small little batteries that go in like flashlights and your Xbox controller and that sort of thing. Now, those batteries have a place, but it's usually inside your toolbox. You generally don't see primary cell batteries being used inside the aircraft. If not, and if it ever is, they're going to be in things like backup batteries for radios and like military applications, or random little applications here or there where they don't need a lot of power. They just need like a little bit to save memory or something to that effect. So you'll very rarely see them in some sort of official capacity, but you'll use them a lot coming and going out of the tool room, that's for sure. And all the test equipment that you're going to end up using, you'll end up using primary batteries that way, or primary cell batteries that way. Most commonly, you're going to use what's called secondary cell batteries. Secondary cell batteries have some sort of construction where the electrochemical reaction inside of the batteries is reversible. Now, inside of aircraft, you're basically going to have one of a couple of different types of batteries. One, you're going to have a lead acid battery. Two, you'll have a NiCad battery, a nickel cadmium battery. You'll have a lithium ion battery or a lithium ion polymer battery. Now, I'll tell you this, I don't think I've ever encountered a lithium ion polymer battery as of yet, but battery technology is rapidly changing, especially with the advent of electric cars. There's a huge market pressure on that industry to innovate, to make them lighter, to make them better, more reliable, and so expect to see a lot of change over the course of your career in battery technology. That being said, the two most common batteries that you're going to encounter is the lead acid battery and the NiCad, the nickel cadmium battery. These batteries typically are constructed very, very similar. It doesn't really matter what manufacturer it is, lead acid batteries or lead acid batteries. They have vertical porous lead plates filled with sulfuric acid. Now, the plates are connected to each other via a device called a cell strap. It's basically like a little bonding strip that connects one cell to the next cell, and they're wired in series. That means positive terminal to negative terminal, then positive terminal to negative terminal, and they're all in series. Now, every cell basically gives a lead acid battery about 2 volts. And there's usually about 6 cells, so therefore there's like a 12-volt battery right here in front of me. Now, there are 24-volt batteries, and you'll see those out in the wide world. But just know that it's about 2 volts per cell. Generally speaking, lead acid batteries are kind of on their way out. They're older, they are more maintenance intensive, they have a lot more hazards associated with them, and you can take the same battery that's 12 volts, that weighs probably 30, 40 pounds maybe. You can get a lithium ion battery. It's more expensive right now, but it's about this big, and it'll do the same amount of power for longer for less weight. The general parts of the battery are usually very similar. This top will pop off, and we're going to do that here in a minute when we go to service the battery. And then it's always vented, because one of the things that will end up happening is with the battery is that you'll end up have off gassing, and you don't want the gas to get trapped inside the battery, because then this basically becomes a balloon. Eventually pops, sprays battery acid everywhere, and then you have like rampant corrosion, and you don't want to get that on your hands. It's a bad day. The batteries also should always be, unless they are sealed, and there is a type of, and probably the most common lead acid battery today is not the serviced battery type, it's the sealed battery type that doesn't have to be serviced, and it won't leak, so it can be inverted, and you don't have to worry about it. These types of batteries, though, that are freely vented, you don't want to tip them over because then they'll leak everywhere. I remember working on a plane one time where they had the wrong type of battery installed, and then they started doing acrobatics, and they slung battery acid basically all over the back end of the airplane. It's not something that you want to do. It was a very expensive mistake to make. So make sure that you have the right battery in the right plane doing the right job. Okay, so by far and away, the more common battery that you're going to deal with in a MRO type environment or heavy commercial aviation or working on business jets and that type of thing is the NiCad. The NiCad years ago started to replace the lead acid battery, and no one's really kind of looked back. They are by far superior in every possible way, and they're more sophisticated. If you'll notice, this one has a cannon plug or two of them on top of them. That will monitor battery temperature. You'll see these on just about every NiCad that you have to work on, and some other applications as well, because one thing that you need to worry about with batteries is thermal runaway. Not so much with lead acid, not so much with NiCads, even though they're still a threat, but definitely with lithium ion. And if you remember from basic electricity, the heat will lower resistance, lowered resistance increases current then runs rampant and can cause a battery fire or explosion. And we've seen that whenever the Boeing 87 rolled out, they had a serious problem with lithium ion batteries because it's the first time it's ever been used. So we're still learning, and that's aviation's a kind of an industry of lessons learned, really. This plug is fairly universal. You'll see it all over the place. Whenever you go to plug up a jet, you're going to want to make sure this thing is strapped down. Notice there's two hooks. Lead acid batteries typically have a strap that goes over them. You could have a strap with this one too, but the more common approach is that you'll have two little bars on these little hooks with like little 5/16 nuts that you torque down to about 120 inch-pounds. It's not really that big of a deal. They are also vented, and we're going to pop this thing open. We're going to let you see the inside of it. And you'll do maintenance on these things, but you generally don't service NiCads. What you'll do is you'll clean the corrosion off these cells right here. So if you'll notice, the cells are put together in series. You can start on one end and just kind of work your way all the way from one to the next to the next. So there's negative, positive, negative, positive, negative, positive. Now I will caution you. I'll tell you a story about whenever I first started. I was at the National Training Center working on a 58, and my job was to do a battery service. So you pull a battery out, you clean out the battery compartment, make sure there's no debris, no corrosion, and then you clean off the top of the cells. Now, in our technical manual in the book, it will tell you to use a non-conductive brush, which we had in our toolbox. Now, as I started to clean this stuff out, just like on this one, there's little bits of corrosion that the brush just wasn't going to take off, and so I whipped out my pocket knife and started scraping it off, thinking that I was going to be super thorough. I was going to be a super mechanic. Well, what ended up happening is I ended up arcing the two of the cells together, and it caused the knife blade to explode in my face. And so luckily, it didn't hurt the battery and it didn't hurt me, and kind of got out of there with minimum cost. But it was a lesson learned. It's be real careful with this stuff because they look just like little plastic sleeves of stuff, but there's a lot of power in those plastic sleeves, and so you don't want to take that take that lightly. All right, these cells are they're filled with nickel hydroxide as the electrolyte with cadmium plates. Generally speaking, like I said, you don't service these batteries. However, some of them you may end up servicing. There's one with the plugs come loose. Depending on the model and era of battery that you're working with. Now, what you want to do is make sure that you check the battery's manufacturer and see what it tells you to do. Most of the time, like I said, these are generally speaking, they're sealed. you'll probably end up having to charge them, but you're not going to necessarily have to actually go and put any sort of like distilled water or anything in there. But you may, depending on, like I said, the model of battery and the era the battery was constructed, because battery technology's come a long way over the past 50, 60 years, and it's going even further now. So you want to make sure that you stay on top of whatever the manufacturer says to do. That's what you want to do with your batteries. All right, so NiCads are a little bit more temperamental than lead acid batteries. Lead acid batteries is kind of like, think of it like your old Model T or like an old Ford truck, that like they're really simple, they're hard to mess up, but they can't really perform like some of the modern batteries can. A NiCad can outperform a lead acid battery in just about every situation. However, they are more temperamental. You don't want to get them too low on voltage, because then they'll off gas. You don't want to overcharge them, because then they'll off gas. They have a condition called voltage depression after being charged and dissipated multiple times, and so they have a life cycle that they need to basically come out and get serviced, and then they can be put back into use. The good part about it is that they're really relatively simple in construction, very relatively cheap to operate. They are extremely heavy compared to a lead acid battery or just about any other type of battery that's out there. And because of that, they'll eventually get replaced with lithium-ion batteries as well. Even if there's no electric cars or whatever, there's still a massive incentive to replace these heavy batteries, because just think about it, like that's probably 100 pounds right there, probably close to it. And every time the plane takes off, that's basically like you're flying an extra child, that you're having to pay for gas and all that good stuff for. So eventually you'll get to a lithium-ion battery that'll be a lot smaller. They are vented, and you want to make sure those vent holes are open, because what you don't want to have to do is like run the battery down, it starts off gassing, and then this swells up and then becomes like a balloon. That can happen also with a lead acid battery. All right, so let's talk about lithium-ion batteries. Now, lithium-ion batteries are fairly new to the aviation game compared to the NiCad and lead acid batteries and the sealed lead acid batteries. They were famously put to use, like I said, in the 787, where they immediately started having fires as soon as they hit the fleet. The reason being is that they're pressurized, for one, or they're kept under pressure, and number two, the electrolyte in a lithium-ion battery is actually flammable. And this is true for even lithium-ion batteries that are used in cars and your boat's trolling motor and all that good stuff. It's all the same technology. So Boeing was the first person to actually put it on aircraft and roll it out. They got to a situation where it got hot, thermal runaway happened, boom, battery fire. Luckily, there's enough safety mechanisms in place to stop the fire from spreading, so it didn't lose the whole aircraft. But either way, the lesson was learned that, hey, look, like a lithium-ion battery can't be handled the same way that a lead acid or a NiCad battery, and so we in aviation have to change the way that we do things based on how technology progresses, and so that's what happened. You can expect in the future to see a lot more lithium-ion being used as that technology progresses, as it gets cheaper, as it becomes more prevalent. I would use a lithium-ion battery in my own airplane. I would replace that little 12-volt battery that probably weighs 20, 30 pounds with a 5 or 6 pound lithium-ion battery in a split, if there was one that was PMA certified. So you can expect to see people taking that same route in the future. All right, the way that we determine whether or not a lead acid battery is fit for use is by measuring the specific gravity of the battery acid inside of the battery itself. Generally speaking, what will end up happening is that you'll measure it out, and we're going to be looking for about 1.2 to 1.3 of the specific gravity based on the hydrometer that you're about to see here in a second. Now, if the hydrometer won't float up enough, we want to add battery acid, and it comes in like a little powder form. You mix in there, and it mixes with what's in the cell and raises it back up. If it's too much, maybe the battery is just done, and it's time to get rid of it and replace the battery. And that's more often than not today with sealed batteries. That's what you would want to do. The only reason that you would actually go and service a battery is if the customer would rather pay you to service the battery rather than just simply replacing the battery with a more modern battery. There could be other like random instances where that happens. That like perhaps there's something specific about that battery to that aircraft that you can't just simply replace it with like a Concorde steel battery that's in most GA airplanes now. Now, if the battery acid is too high, then what you want to do is remove a little bit of that fluid and then place distilled water back into it, so that way it's serviced up. But you always want to fill up the cells to their proper level per the manufacturer's instructions. But you want to have the specific gravity right as well. So you have to play with that a little bit to try to get it right. It's a messy process, and frankly, it's an antiquated process that's slowly dying. But it's still on the ACS, and still you may encounter that out in the wide world out there somewhere. So you need to know how to do it. On top of that, it's just a good skill to have, because guess what? Most of your lawnmower batteries are still old lead acid batteries that aren't sealed. Okay, so the first thing we need to do is look at the tool that we're going to be using. This is called a hydrometer, a hydrometer. What it's going to be measuring is the specific gravity of the acid in the battery. Notice that on the ballast there's a graded scale that goes up to about 1.8 or so. So we're going to attach the whichever straw that you deem appropriate, and then we're going to stick it into your battery. Now here is just a bottle of water. It's just regular tap water to show you what regular water looks like. Notice that the ballast doesn't float at all. It sits at the bottom of the hydrometer. Now, when you're opening a battery, you want to be careful of a couple of things. Take a screwdriver and place it underneath the cap and gently twist it, so that way you don't deform the lid or damage the battery. Once it gives way, it should just pop up in your hands just like that. Set both caps aside so you know which place they go back to, because you want to always return things back to exactly how you found them if at all possible. When you go to do the measurement, stick the hydrometer down into the cell and suck up enough fluid to float the ballast, so that way you can get a proper reading. We're going to check the reading right here, and it should read somewhere that where the water line hits the numbered tape right there should be between 1.2 to about 1.3 on most batteries. But always refer to the manufacturer's specification of what the specific gravity of the battery acid should be. Once you're done, just squirt the battery acid and water combination back into the cell, and then reverse the whole process. Put the caps back on, make sure that they're sealed, so that way no battery acid can spill out. Remember, this is sulfuric acid. It can burn your skin, and it can corrode metal very quickly and very easily. Okay, let's talk about the life cycle of a battery. A battery is considered good so long as it can discharge 80% of its rated value. So anytime it goes below 80%, the battery is just considered no good anymore. So how long does it take for a battery to get to that point? Well, it really depends on a couple of things. One, the battery itself. Most batteries are rated for a number of cycles, meaning being charged and dissipated up to like the lowest I've ever seen is about 500, but some of them are rated for 1,000, 1,500 cycles, and they could go even higher, longer than that. Just depends on the battery itself, the conditions the battery's in, and how well it's taken care of. So some of the things that you want to be careful with to maintain a battery for as long as you possibly can is not to overcharge it. If you overcharge it, you can cause a condition called excess sulfation. Excess sulfation is the buildup of crystals on the battery plates and will ruin a battery. Another one is that you don't want it to rapidly charge it too often or discharge it too often, because what will end up happening is the plates inside of there will get so hot from all those electrons moving through it so fast, and that will cause it to shed the active material that's actually baked onto the plates. Now, the battery will be able to continue to work with that excessive charging or discharging, because the plate will still have active material on it, but what will end up happening is that excess of material will float around in the battery and eventually short the plate. And once the plate gets shorted, it'll internally discharge all of its electricity. So the plate will gather electrons, and then some of the active material comes and shorts between two plates, and then it just discharges into the next plate, and it basically kills the battery at that point. So you want to avoid those two cycles. However, other than that, batteries are actually fairly simple devices. It's always going to be a plate, some electrolyte, and then you charge it. It doesn't really matter what the battery is made out of. That's the basic recipe for any battery. The innovation inside of the progression that we're seeing is the different materials that are being used in different ways. So like like we talked about the lithium ion battery being pressurized. That's not something that you necessarily even see even with sealed batteries. And so like that gives it a slight advantage, and as these slight advantages add up, we'll have to stay on top of how batteries progress, so that way we know best how to care for them and how to best make sure that we don't mess them up or cause some sort of like fire or anything else like that. But yeah, that's batteries. Okay, so battery ratings can get a little bit tricky if you don't really understand amp hours. So all an amp hour is so 1 amp hour is how can the battery produce 1 amp for 1 hour at its rated voltage. All right, so if you were to say like, hey, look, I have a 120 amp hour battery, you would say, okay, well, it can produce 120 amps per 1 hour, or it could produce 1 amp for 120 hours. And you can start to establish the mathematical relationship between those two kind of like goalposts, and try to figure out exactly how many amps do you need for how many hours. Now, generally speaking, this is kind of a rule of thumb, because what ends up actually happening is that like you need a lot of amps in a little bit of time for like battery start or aircraft starting and things like that. That means that the battery can be discharged way faster than what you would actually be rated for, because it's going to be just drawing way more power. If it's a 120 amp hour battery and you ask it for 500 amps, you can do the math on how like few minutes that battery is going to be able to produce 500 amps, and it's not going to be very long. But that's what we do with cranking batteries. We ask it for a lot. It gives it to us, but it can only give it to us for so long. So at best, you got 3, maybe 4 cranks, and then that battery is going to start to get like really, really, really weak. One of the things that you want to do whenever you're cranking an aircraft after you've cranked it is watch the amp meter, and you should see a load on it. And then as the battery charges up, it'll start to trickle off. Because remember, like anything electrical, it's just like water. So that like if you have like the generator that's producing like so much water, and it trickles over into the battery that's only over here, eventually they start to get like that. And as they get closer and closer, that electromotive force starts to dip off. The pressure starts to slow down. As it slows down, eventually they stabilize, and there's no movement at all. But it's not a off and on. It's a very much a graded scale. So that's something to keep in mind.